primary advantage of a 4-pole automatic transfer switch, or ATS, over a 3-pole ATS lies in its ability to break the neutral connection. This seemingly simple difference offers several significant benefits in terms of safety, performance, and system reliability. Firstly, improved safety is a key advantage. When the neutral is broken, it eliminates the risk of accidental ground faults. Ground faults occur when there's an unintended electrical connection between a live conductor and ground. This can create a dangerous situation, potentially leading to electrical shocks. By isolating the neutral, a 4-pole ATS effectively mitigates this risk. Secondly, enhanced surge protection is another notable benefit. Surges, or voltage spikes, are transient overvoltage events that can damage sensitive electronic equipment. These surges can propagate through the electrical system, including the neutral line. By breaking the neutral connection, a 4-pole ATS improves surge protection by eliminating the path for voltage spikes to travel through the neutral line, thereby safeguarding connected equipment. Thirdly, a 4-pole ATS allows for separate control of line and load neutrals. In some electrical systems, it may be desirable to isolate the neutral of the power source from the neutral of the load. A 4-pole ATS provides this capability, allowing for more flexibility in system design and operation. Now let's delve into the specific reasons for breaking the neutral in an ATS application. One crucial reason is to eliminate ground loops. Ground loops occur when multiple electrical paths exist between different parts of a system, creating unwanted currents to flow through the grounding conductors. These currents can cause various problems, including noise, interference, and equipment malfunction. By breaking the neutral connection, a 4-pole ATS prevents ground loops from forming, improving system stability and performance. Another reason for breaking the neutral is to reduce harmonic distortion. Harmonics are unwanted frequency components that can be generated by nonlinear loads, such as variable frequency drives, electronic ballasts, and uninterruptible power supplies. These harmonics can pollute the electrical system, causing interference, overheating, and equipment damage. Breaking the neutral helps mitigate harmonic distortion by preventing harmonic currents from circulating through the neutral conductor. Furthermore, breaking the neutral improves fault detection capabilities. In the event of a ground fault, a 4-pole ATS can more accurately identify the faulty circuit by isolating the neutral. This allows for quicker and more precise fault clearance, minimizing downtime and improving system safety. In addition to these technical advantages, code requirements may mandate the use of a 4-pole ATS in certain applications, particularly in commercial or industrial settings. These requirements are often put in place to ensure safety and compliance with electrical codes and standards. To summarize, a 4-pole ATS offers several advantages over a 3-pole ATS, including improved safety, enhanced surge protection, separate control of line and load neutrals, elimination of ground loops, reduction of harmonic distortion, and improved fault detection. These benefits make a 4-pole ATS the preferred choice for many critical applications where reliability, safety, and power quality are paramount. It's important to consult with a qualified electrical engineer to determine the appropriate type of ATS for a specific application, taking into account the specific requirements and code regulations. The decision between a 3-pole and 4-pole ATS should be based on a thorough evaluation of the system's needs and potential risks. Choosing the right ATS can significantly improve the overall performance and safety of the electrical system. When we consider the technical specifications, it is imperative to also think about the grounding system configuration. The grounding system plays a vital role in the effectiveness of both 3-pole and 4-pole ATS configurations. A properly designed grounding system ensures that fault currents have a low impedance path to return to the source, facilitating the operation of overcurrent protection devices. In a 4-pole ATS, the neutral conductor is switched, which means that the neutral connection between the source and the load is broken when the ATS transfers from one source to another. This is particularly important in systems with sensitive electronic equipment, as it prevents circulating currents and ground loops that can cause interference and damage. In contrast, a 3-pole ATS does not switch the neutral conductor. The neutral remains connected between the source and the load at all times. While this may simplify the wiring and installation, it can also increase the risk of ground loops and harmonic distortion. Furthermore, the selection of an ATS should also consider the type of loads being served. Nonlinear loads, such as those found in modern electronic devices, can generate significant harmonic currents. These harmonic currents can flow through the neutral conductor and cause overheating, voltage distortion, and other power quality problems. A 4-pole ATS can help mitigate these issues by preventing harmonic currents from circulating through the neutral conductor. Another important consideration is the available fault current at the installation location. The ATS must be able to withstand the available fault current without sustaining damage. The fault current rating of the ATS should be clearly indicated on the nameplate and should be verified to be adequate for the application. In addition, the ATS should be equipped with appropriate overcurrent protection devices to protect against short circuits and overloads. These overcurrent protection devices should be coordinated with upstream and downstream protection devices to ensure proper selectivity and coordination. The installation of an ATS should be performed by qualified electrical personnel in accordance with all applicable codes and standards. The ATS should be properly grounded and bonded to ensure a safe and reliable installation. Furthermore, regular maintenance and testing should be performed to ensure that the ATS is functioning properly. This includes visual inspections, installation resistance tests, and operational tests. The results of these tests should be documented, and any necessary repairs or replacements should be made promptly. The cost of a 4-pole ATS is generally higher than that of a 3-pole ATS. However, the additional cost may be justified by the improved safety, performance, and reliability that a 4-pole ATS offers. The decision to use a 4-pole ATS should be based on a careful evaluation of the system's needs and potential risks, taking into account the factors discussed above. In addition to the technical considerations, it is also important to consider the regulatory requirement. Many electrical codes and standards require the use of a 4-pole ATS in certain applications, particularly in healthcare facilities and other critical environments. These requirements are put in place to ensure the safety and reliability of the electrical system. Therefore, it is important to consult with a qualified electrical engineer to ensure that the ATS selection meets all applicable regulatory requirements. In summary, the selection of an ATS is a complex decision that requires careful consideration of various factors. These factors include the grounding system configuration, the type of loads being served, the available fault current, the regulatory requirements, and the cost. A qualified electrical engineer can help evaluate these factors and recommend the appropriate ATS for a specific application. Now, let's elaborate more on the grounding system configuration and its interaction with the automatic transfer switch. The grounding system, as mentioned earlier, is a critical component of the electrical system. It provides a low impedance path for fault currents to return to the source, which allows overcurrent protection devices to operate and clear the fault quickly. There are several different types of grounding systems, including solidly grounded, impedance grounded, and ungrounded systems. The type of grounding system used will affect the selection and operation of the ATS. In a solidly grounded system, the neutral conductor is directly connected to ground at the service entrance. This provides a low impedance path for fault currents, which allows overcurrent protection devices to operate quickly. However, a solidly grounded system can also be more susceptible to ground loops and harmonic distortion. In an impedance grounded system, a resistor or reactor is inserted between the neutral conductor and ground. This limits the amount of fault current that can flow, which can reduce the risk of ground loops and harmonic distortion. However, an impedance grounded system may also be more difficult to coordinate with overcurrent protection devices. In an ungrounded system, the neutral conductor is not connected to ground. This eliminates the risk of ground loops and harmonic distortion, but it also makes it more difficult to detect ground faults. An ungrounded system typically requires the use of ground fault detectors to identify and isolate ground faults. The selection of an ATS should be based on the type of grounding system used. In a solidly grounded system, a 4-pole ATS may be preferred to prevent ground loops and harmonic distortion. In an impedance-grounded system, a 3-pole ATS may be sufficient, as the impedance in the grounding system will limit the amount of fault current that can flow. In an ungrounded system, a special type of ATS may be required that is designed to work with ground fault detectors. In addition to the grounding system, the type of loads being served will also affect the selection of the ATS. As mentioned earlier, nonlinear loads can generate significant harmonic currents. These harmonic currents can flow through the neutral conductor and cause overheating, voltage distortion, and other power quality problems. A 4-pole ATS can help mitigate these issues by preventing harmonic currents from circulating through the neutral conductor. Another type of load that can affect the selection of the ATS is a motor load. Motor loads can draw a large amount of current when they start, which can cause voltage dips and other power quality problems. An ATS that is designed to handle motor load should be selected to minimize these power quality problems. The available fault current at the installation location is another important consideration. The ATS must be able to withstand the available fault current without sustaining damage. The fault current rating of the ATS should be clearly indicated on the nameplate and should be verified to be adequate for the application. Furthermore, the ATS should be equipped with appropriate overcurrent protection devices to protect against short circuits and overloads. These overcurrent protection devices should be coordinated with the upstream and downstream protection devices to ensure proper selectivity and coordination. The installation of an ATS should be performed by qualified electrical personnel in accordance with all applicable codes and standards. The ATS should be properly grounded and bonded to ensure a safe and reliable installation. Furthermore, regular maintenance and testing should be performed to ensure that the ATS is functioning properly. This includes visual inspections, insulation resistance tests, and operational tests. The results of these tests should be documented, and any necessary repairs or replacements should be made promptly. The cost of a 4-pole ATS is generally higher than that of a 3-pole ATS. However, the additional cost may be justified by the improved safety, performance, and reliability that a 4-pole ATS offers. The decision to use a 4-pole ATS should be based on a careful evaluation of the system's needs and potential risks, taking into account the factors discussed above. Moreover, the selection process of an ATS, either 3-pole or 4-pole, must adhere strictly to the National Electrical Code (NEC). Several articles within the NEC pertain directly to transfer switches, emergency systems, and the proper handling of neutral conductors. Firstly, NEC Article 700.12 addresses the wiring of emergency systems. It stipulates requirements for the separation of emergency system wiring from other wiring systems to minimize the likelihood of a fault affecting both normal and emergency power. Secondly, Article 700.5 discusses the capacity and rating of emergency systems. The transfer switch, as a critical component of the emergency system, must be rated to handle the full load it is intended to serve. This includes consideration of inrush currents from motors or other inductive loads. Thirdly, NEC 250.30 provides guidance on grounding and bonding for separately derived systems. This is particularly relevant when the transfer switch is used to switch between a normal power source and an emergency generator. The grounding and bonding must be done in accordance with the NEC to ensure a safe and effective ground fault path. Fourthly, the decision to switch the neutral conductor, which is the key difference between a 3-pole and 4-pole ATS, is addressed in NEC 250.30 The NEC permits the neutral conductor to be switched under certain conditions, such as when necessary to prevent objectionable current flow or to improve system performance. However, it also mandates that the neutral conductor must be reliably grounded at both the source and the load. Fifthly, NEC 310.15 outlines the requirements for conductor ampacity. The conductors used in the ATS and its associated wiring must be sized to carry the intended load current continuously without exceeding the temperature rating. This is essential to prevent overheating and potential fire hazards. Furthermore, NEC 408.3 addresses the identification of neutral conductors. The neutral conductor must be clearly identified throughout the electrical system, typically with white or grey insulation. This ensures that electricians can easily distinguish the neutral conductor from other conductors. In addition to the NEC, other industry standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, may provide additional guidance in the selection and application of ATS. These standards often address specific aspects of ATS performance testing and maintenance. Understanding and adhering to these codes and standards is paramount for ensuring the safe and reliable operation of an ATS. Failure to comply with these requirements can result in serious consequences, including electrical shocks, fires, and equipment damage. Therefore, it is crucial to consult with a qualified electrical engineer who is knowledgeable about the NEC and other relevant standards when selecting and installing an ATS. This expert can help ensure that the ATS is properly sized, installed, and maintained in accordance with all applicable requirements.